I'd like to continue our conversation about how to build Lewis dot structures and talk about polyatomic ions. Now, these are compounds that are ions, but they are composed of more than one nonmetal atom. And so it's a molecule that's covalently bonded together that has an overall charge to it. So, for these situations, when we're building the Lewis dot structure to describe it, we are going to add electrons if it's a negative charge and remove electrons if it's a positive charge. And you're going to add them or remove them in any way that you need to make the structure work. So, like, it doesn't have to come from a specific atom necessarily. So let's look at the Lewis dot structure of cyanide. And so this, we've looked at hydrogen cyanide. Now this is if there's no hydrogen. So it has a negative charge. So this means automatically I'm going to add one electron anywhere I want. I'm not going to do that till the end though. I'm going to build this structure until I hit a point where I'm like, I have one unpaired electron that I can't do anything with, and I'm going to add my extra electron there to pair it up so it has an octet. So when I do this, I've got it written out here, typed up, but what I've done is I've brought my two element symbols, my carbon and my nitrogen together and formed a bond between them. Ah, now, I'm going to need to pair these things up. There's no way I'm at close to an octet, and I'm not going to get to add any extra elements, right? So I'm going to need to use multiple bonds to reach my octet. So I can pair up these two, I can pair up these two, and that's just going to leave one unpaired electron left. So instead of bonding another atom to it like we did in hydrogen cyanide, I get to add that extra electron to pair up with the carbon. And this brings us to one of our few situations where carbon has a lone pair, and it's because it's an anion. So what I get when I redraw this is this picture where I have a triple bond between carbon and nitrogen. I have a lone pair on carbon and a lone pair on nitrogen. And to indicate that I had to add an electron to make this all work and it has an overall charge, I am going to put it in brackets and add a negative symbol. So I should have 4 valence electrons from carbon, 5 from nitrogen, plus 1 that gives it the -1 charge for a total of 10 valence electrons at the end. Let's do another example. Let's do hydroxide. This is another really common one. So here I'm going to have oxygen, which will have 6 valence electrons. Great. I'll have hydrogen that has 1 valence electron, and I'll have my extra electron that I get to place somewhere. So I'm going to pair up this hydrogen and this oxygen, and now I'm left with just one unpaired electron. And so I'm going to use my extra electron to create a lone pair. So the unpaired electron isn't alone. Because before I add my extra electron there, I only have 7 valence electrons around my oxygen. And so now I can redraw this as my oxygen and hydrogen bonded together. And I have 3 lone pairs around my oxygen for a total of 8 electrons around oxygen with the shared 2 to hydrogen. If it feels overwhelming to like track these electrons when we're doing polyatomic ions, one of the things I like to do is actually make all of my extra electrons stars and put them in. And that kind of helps me go, oh yeah, I added one. I should put a negative charge in brackets around it. Sometimes it helps.